Hi, in this video I will tell you about the features of another EvoLogics product, our SDM modem. I will also show you SDM implementation of Janus protocol, the NATO standard for underwater communication. Let us begin with the basics. What is SDM modem? SDM stands for Software Defined Modem. It provides the standard functionality of an EvoLogics acoustic modem, and moreover, it has an extra ability to send and receive user-defined waveforms and forward them to the user's software for processing. What are the applications for SDM modems? These are development of signal modulation methods and their prototyping, enabling compatibility with third-party devices on a user level. For devices with a built-in USBL antenna, another application is developing new methods for ultra-short baseline positioning. And last but not least, with SDM modem, you can implement sonar functionality on acoustic modem hardware. There are two ways to switch a software-defined modem into SDM mode. First, you can use the standard modem interface and send the ATP command. So I connect to the standard port 9200 and send ATP command. So we got initiation fee. This is the right SDM state. Another way is to send a stop command to specific port. Port number 4200 opens specifically for SDM Shell commands. In this case, the modem will automatically switch to SDM mode. In SDM mode, the modem is controlled by binary commands described online here. So you can go to GitHub, EvoLogics SDM Shell wiki, and see the list of supported commands. The commands are the config, to set SDM related configuration parameters, reference, to set up the reference waveform for detector. Then we have the stop command to stop waveform reception or transmission, TX to transmit the waveform, and RX to receive the waveform. This is the first group of commands. They are related to modem functions. The second group is following. We have USBL config to set SDM USBL related configuration parameters, USBL RX to download waveform from receivers of USBL grid, sys-time to get transmission or reception related clock values, and so on. So the second group is for working with USBL and for synchronizing of several devices with an external signal. These commands are out of scope of this video and will be addressed in the future. For the majority of tasks, there is no need to implement an SDM protocol. It is enough to use the free SDM Shell application we developed. It is available on GitHub. In all the examples, we will use the SDM Shell for working with the modem. The easiest way to send waveform using an SDM modem is to form a file with signal samples in ASCII format. I can show you such example. So the syntax is one sample per line with a float number in range of -1 and 1. The sampling rate is 62,500 for 717 kHz models and 250,000 for the rest of EvoLogics modems. I run SDM Shell connected to modem 171. And first we have to configure the modem. To do that, we use help to see the format of config commands. So we can control threshold, gain, source level, and preamplifier gain. Source level 0 corresponds to the maximum transmission signal level and 3 to the minimum. So let us configure using 3. And now we can transmit a signal using TX command. And once more. To receive a signal, you must use the RX command. Reception begins at the moment when the signal detector is triggered. To set up the detector, one must use the ref command. It defines a reference signal of 1024 samples. To generate a reference signal, you can use the same format as for signal transmission we demonstrated earlier. Let us use a linear chirp 717 kHz recorded into a file. I prepared such a reference signal and can display it in GNU plot. So that's our reference signal. And now I connect to modem 2 on the right side of my terminal. Configure it first, like we did before. And now I type the ref command and the name of the recorded reference file. Data. So, and now we can switch into the reference signal detection mode. To do that, we use the RX command, where we have to set the number of received signal first and the file name where the received signal should be saved. First, I will demonstrate you the file I'm going to transmit. This signal consists of 10 chirps. At the first beginning, there is a reference signal, and the rest of the signal will fill with 9 chirps, one after another. So there are 10 chirps in total. I can plot you and with GNU plot to show you the signal I'm going to transmit. Here we go. We have 10 chirps, one after another. So to configure modem 2 to receive a signal, I'm typing the command RX, total number of samples. In our case, these are 11,264 samples, and I'm going to record it to a RX raw file. So now we see the RX report. It means that SDM mode is configured and ready for signal reception with the reference defined. And modem 1 transmits signals including 10 chirps. So here we go. Modem 2 received 11,264 samples, and we can plot it to see what we got. So let us note that the received signal contains 9 chirps. This is because signal reception begins at the moment of signal detection, which corresponds to the moment when the reception of the reference ends. In detection mode, preamplifier gain is controlled by automatic gain control. From the moment of signal detection till the end of signal reception, gain is fixed at the value set by automatic gain control at the moment of signal detection. A 30-bit clock value is available for tasks that require estimation of signal propagation time at the user level. The modem returns clock values with systime commands available in SDM Shell. Systime commands output 4 values that corresponds to current system time, last signal reception, so the moment of signal detection, the time of last signal transmission, beginning of transmission, and the last value of sync-in. Sync-in is a synchronous signal which can be used to synchronize multiple modems in a network or modems connected to the PC. So I will show you how it is working. So we have systime, we have current time, TX time, RX time. Let us transmit and check systime once more. So we see the current time changed and the transmission time also. Let us do it on the receiver side. I will send and check systime and do it once more. this time. We see the value changed. Some applications might require turning off the signal detection procedure. This can be performed with the config command, where you set the detection level to 0. So let us do it. Config the modem with threshold 0. So in this case, setting a reference signal is not needed anymore, and signal reception will begin at the moment the modem receives the RX command. So we see it's started, and we recorded file to file RX0. Let us display it. So we see only noise. Let us now transmit the signal including 10 chirps and receive the signal. And let us plot. So we see first noise and then the chirps. Next, I would like to demonstrate our implementation of JANOS protocol and SDM modem. JANOS is NATO standard for underwater communication. It is defined in 944 till 13.44 kHz frequency range. Therefore, our 717 modem is well suitable for implementing this standard as it operates in a wider range. The JANOS reference implementation, JANOS-C, can be downloaded online. So you can follow the link janoswiki.com. Our open implementation allows to detect the beginning of JANOS data packet as well as demodulate and modulate JANOS packet. By request, we can provide our JANOS-C patch set for integration with SDM Shell. To send a JANOS packet, let us use JANOS TX software. I have downloaded in my directory. To ensure compatibility with SDM Shell, the format must be S16 and the sampling rate must be set at 62,500. To transmit a JANOS signal using SDM Shell, I am going to generate a signal with JANOS TX and record it into the TX raw file. To generate a signal, we have to run JANOS TX with a configuration file. Let us take a look at this JANOS TX JANOS configuration file. So what we see here is S16 format, the sample rate, and the output file we are going to record. So now let us generate JANOS signal using the config file. So JANOS TX minus config file, and then this config file. So look, we have the generated TX raw file in this directory, and let us transmit the generated TX raw signal file with SDM modem. So we run SDM Shell connected to SDM modem 1 on the left side, and like always, configure it first and transmit the recorded file. So we can hear the transmission. Great. Now let us talk about JANOS reception. During of the JANOS preamble is slightly longer than our standard reference signal, length of 1024 samples. Therefore, it is not possible to use our standard signal detector to receive JANOS signals. We implemented detection of JANOS preamble on the SDM modem level. Signal detection is performed on our low modem hardware level. Once a JANOS preamble is detected, the modem estimates the Doppler shift and the first symbol's reception offset. These parameters are transferred to our modified JANOS RX that skips signal detection and begins with demodulation straight away. When triggered, SDM Shell automatically launches JANOS RX Shell script with the detector's parameters. In turn, it starts up JANOS RX in demodulation mode with detection skipped. So let us do it. RX JANOS. So we are waiting, and now modem 1 can transmit a JANOS signal.
So what we see on the reception side is a baseline packet. So we see sampling frequency, the version number, CRC, the cargo, and so on. Another application of SDM modems is SDM USBL. SDM USBL supports the same SDM Shell command set as an SDM modem. SDM Shell includes the USBL config command that must be used to configure reception of signal on USBL channel. So first we can take a look to the USBL config format. So we see what has to be configured. It is delay, samples, gain, and sample rate. Another command, USBL RX, must be used for each USBL channel separately to switch the channel into reception mode. So I prepared a configuration file. So what we see here is the config and RX commands we used to work with an SDM modem before. In addition, we use USBL config and 5 times USBL RX for each USBL channel. So look at this graph. The reception on each USBL channel looks as follows. We see 5 channels with different amplitudes and different time arrivals on the x-axis. These signals arrival times are used to calculate the angle of the positioning target and the propagation time we calculated before. The propagation time value helps us estimate the distance to the target.
I hope this video was useful to you. Thank you for your attention.